Thanks for the invitation. Yeah, thanks a lot for the invitation to speak at this conference in Oslo. The topic of this talk is a bit more of a formal nature, but it might have interest for people that are interested in these Weil cohomology theories, because it gives a general way to construct examples of cohomology theories that generalize the Ram cohomology. So they may have properties similar to the Ram cohomology, which is known to be a Weil cohomology theory. And they come from geometry. They are constructed using differential operators on varieties. So in this sense, they come from geometry. It's divided into 4 parts. So the introduction. So we start with a commutative unital ring, K, and a K algebra A, and an A module E. And then there are several types of connections we can study. So a Kosul connection, or an ordinary connection, is just such a K-linear map from E to the E tensor of the Kähler differentials, which satisfies this multiplicative property for all A in A and E in E. And such a connection is a differential operator of order 1 from E to this tensor product. We can dualize the situation and instead consider a map from the Lie algebra of K-linear derivations of A into the K-linear endomorphisms of the A module E. Such a covariant derivative is an A-linear map satisfying this derivation property when it comes to when X is a vector field, A is a function, and E is a section of the bundle. And then we can define the curvature of such a covariant derivative in terms of this formula. And we say that the connection is flat if and only if the curvature is 0. This is if and only if this connection is a map of Lie algebras. So derivations, this is a Lie algebra. The endomorphisms is a Lie algebra, and the connection is flat if and only if this is a map of Lie algebra. And then we can define there is this generalized universal enveloping algebra for this situation. So we can define a filtered associative ring U A der Ka with the property that the category of modules on this associative ring is equivalent to the category of flat connections on this module E. And this ring has a filtration. And when the module of derivation is a projective module over the base ring, there is this Poincaré-Birkhoff-Witt isomorphism. And here, this associated graded ring is the associated graded ring of this enveloping algebra with respect to this, there's this filtration. So this is called the Poincaré-Birkhoff-Witt map, and this map was proved to be an isomorphism in the 60s by Lie-Rinehart in his thesis. So we want to generalize this construction to the case of a non-flat connection. So this isomorphism only holds when this connection is flat. And then we define L star is the module of the derivations. And we choose any 2 co-cycle for this L star with values in the ring A. And this is a 2 co-cycle with respect to this the Lie-Rinehart complex. So the Lie-Rinehart complex is a complex similar to the de Rham complex, which was studied by Rinehart in his thesis. Then we construct a abelian extension. And then there is a result saying there's a 1-to-1 correspondence between flat connections on this abelian extension and connections where the curvature has curvature type F. And then there is this generalization of the classical enveloping algebra of L, where we twist by this cocycle F. So this generalization has the property that there is an equivalence of categories between the categories of modules on this ring and connections of curvature type F. And a connection, when it has curvature type F, This is a particular case of a non-flat connection. And in this more general situation, there is, when this L star is a projective A module, there is a similar Poincaré of width isomorphism for this more general algebra. And this was proved quite recently in 2015. And this algebra, this generalization, it recovers, it's kind of, when you let F be the 0 to co-cycle, then you recover this algebra of Lie-Rinehart. So this, when we just vary this 2 co-cycle, we get a family of enveloping algebras parameterized by this space of 2 co-cycles. And in fact, it's parameterized naturally by the H2, by the cohomology group. Because if we two co-cycles representing the same cohomology class, the 2 corresponding algebras are canonically isomorphic. So you get a family of enveloping algebras parameterized by this cohomology group. And this algebra, it has few 2-sided ideals. In the case of the polynomial ring and the space, the Lie algebra of derivations, and if you let F be the 0 2 co-cycle, then it follows this enveloping algebra is the Weil algebra of, it's generated by these variables and these partial derivatives. And this is a simple ring. It has no non-trivial 2-sided ideals. So any simple module on this ring correspond to a 2-sided ideals in this enveloping algebra and such an isomorphism. We can realize E as a quotient by these 2-sided ideals. So we can, in a sense, we can use these ideals in this algebra to construct non-trivial classes of such non-flat connections. Okay, so now we're going to try to generalize this to the set case of non-flat connections. So if K is any commutative base ring, A is any K algebra, then we look at the direct sum, A plus the Lie algebra of derivations. And we choose a 2 co-cycle for this Lie algebra with values in A. And this is again the Lie-Rinehart complex. And then we define a twisted product, a Lie product on this direct sum. So we twist by this 2 co-cycle here. And then we define a left and right A module structure on D. So the left structure is the trivial structure, and the right structure, then we let this vector field X act like this. This is a non-trivial right A module structure on this. And these are compatible, so it gives this module D the structure of an A tensor A module. And then we define a map, just a projection map, onto the Lie algebra of derivations. And then with this Lie product, this map is a map of K Lie algebras. And then we have this canonical element, 1, 0, in this module D. So then the proposition says that the map, this projection map, if we give the Lie algebra of derivations the trivial right A module structure, it follows this projection map is a map of A tensor A modules and K Lie algebras. And then we have these 2 compatibilities with the Lie product and the right and the left A structure. So this first equation here, it says that D as a left A module is a Lie-Rinehart algebra. And then this second equation, it gives a relationship between the left and the right structure. If we let C act from the right, it is equal to C acting from the left. And then we have to act via this vector field and multiply with this canonical element I. this you can check. So what we have constructed is from this ring A and this 2 cocycle, we have constructed a K Lie algebra and an A tensor A module, and this projection map and this canonical element. And these satisfy this the above axioms. And then we can generalize this to the case of what we shall call a D-algebra, or an algebra of differential operators. So such a D-algebra is a 5-tuple. It's an L, alpha, pi. There's a Lie product, and then there is this canonical element. So L, it's an A tensor A module, and K Lie algebra. This alpha is a map from L to the previously defined D1FA for some 2 cocycle, which is a map of K Lie algebras and A tensor A modules. The map pi is a projection map onto the Lie algebra of derivations, which is a map of K Lie algebras satisfying this commutation property. The element D is a central element in the Lie algebra with the following property. And these are the same equations as we saw in the case of this D1FA. So this first equation says there is a relation between the left and the right structure. So the right structure equals the left structure, and then you let this U act as a vector field on this element C, and then you multiply this with this central element D. And then you have this second condition, which is similar to the condition for a Lie-Rinehart algebra. So in particular, this L with the left A module structure is a Lie-Rinehart algebra. So such a D-algebra is a Lie-Rinehart algebra equipped with some additional structure. The structure of a right A module, and then you have this central element and such a map onto this twist D1FA. And then we can define, in this generalized setting, we can speak about connections. So a connection, if L is a D-algebra and E is an A module, a connection is just an A tensor A linear map. So we do not ask this connection to satisfy some derivation property. We just say that it's supposed to be A tensor A linear. And this derivation property is built into this right A module structure. So this NKA, it has a left and right A module structure. So in particular, it is an A tensor A module. So this row, as if it's a connection, if and only if it's a map of A tensor A modules between these two canonically defined A tensor A modules. And a map of connection is just a map commuting, map of A modules commuting with these actions of this row F and row E. So it's just a map of A module respecting this structure. And examples, kind of the most, well, for any Lie-Rinehart algebras and any such 2 cocycle, we can construct a pullback cocycle as follows. And we can define a Lie product on this abelian extension as follows, just by using the pullback 2 cocycle. And we can define a left and right A module structure. And we can define these maps, alpha F and pi F. Alpha F is just, well, it's U, and then we'll let it, since L is a Lie-Rinehart algebra, there's an anchor map to the derivations. And then we project it onto the derivations. Then this gives a functor. There's a functor from the category of Lie-Rinehart algebras. It depends on this 2 cocycle to the category of D-algebras by sending this Lie-Rinehart algebra to this. So when you choose such a two-core cycle, there is a functorial way to construct such a D-algebra on this Lie-Rinehart algebra. You make this abelian extension, and then you define this this new Lie product and this additional right A module structure. This is a functor. So in particular, to any Lie-Rinehart algebra, you can just choose the 0 two-core cycle. Then you get a canonically a D-algebra and such a map of K Lie-algebras and A tensor A modules. So now, if this is if L is a D-algebra and L star a Lie-Rinehart algebra, and E left A module, and let C just be an A-linear endomorphism of E. And we can generalize the notion of connection to the condition an LC connection. So an LC connection is a left A-linear map from L to the endomorphisms of E, where for any vector field X, it satisfies this formula. So there is a twist with respect to this endomorphism here. And we can do the same for the Lie-Rinehart algebra. We say an L star C connection is a left A-linear map satisfying this formula. So here we have twisted with this endomorphism. So if C is the identity map, we get a classically defined connection on this Lie-Rinehart algebra. So an L-id connection is an ordinary connection. And then there's a lemma. If we have a Lie-Rinehart algebra and we have this two-core cycle, then we can look at the corresponding D-algebra. Then there is a one-to-one correspondence between LC connections on this Lie-Rinehart algebra and maps of A tensor A modules on this corresponding D-algebra. So we may, from any such, well, from connections on the Lie-Rinehart algebra, we can construct connections on the corresponding D-algebra. And this is functorial. So here's the map. We just take rho of UC, and then we let U act via this endomorphism C. This is the map. And you may check that this map is A tensor A linear. This is not a difficult computation. So from each connection on this Lie-Rinehart algebra, we get a connection on the corresponding D-algebra. So now what we want to do now is to try to construct the enveloping algebra of such a D-algebra. So we start with this D-algebra. So L is an A tensor A module and a K Lie-algebra. We have these two maps. We have the Lie product and we have this central element Z. And then we have an abelian group E. And we let R be an associative K algebra with K in the center of R. And then we define the tensor product of L with itself J times over this base field K. So the original algebra A is a commutative K algebra over some base ring K. So by definition, T0 equals K, and T star is the tensor algebra. So it's just a direct sum of all these abelian groups. So there is an equality of sets. So K linear maps from L to this associative K algebra R. This is by definition this, well, this is by definition, but it is the same as the K algebra maps from the tensor algebra to R. This is the universal property of the tensor algebra. So an abelian group E, it's a left module on this tensor algebra if and only if there is a map of rings from the tensor algebra to the ring of K-linear endomorphisms of E. So hence the abelian group by this equality here, it follows the abelian group E is a left module on the tensor algebra if and only if E is a K module and there is a map of K modules from L to the endomorphisms of E. Okay, so let's now L be a D algebra, and let AB be an A and UV be elements in L. Then we construct a two-sided ideal in this tensor algebra. It's generated by this canonical element Z minus 1, and then these two elements, AU here, and this element here. And then we define the enveloping algebra of this D algebra to be the quotient of the tensor algebra by this two-sided ideal. And there is a canonical projection, canonical map from the D algebra into this enveloping algebra. And now we take any two-sided ideal in this enveloping algebra and we define the enveloping algebra with respect to this ideal to be the quotient. Then we get a canonical map P tensor I from L into this generalized enveloping algebra, this quotient. And then we define the category of associative unital K algebras R containing K in the center, where this R has the structure as a left A tensor K A module. And maps in this category are maps of unital K algebras and A tensor A modules. And we let L be a D algebra, rho be a K linear map, and then we let T rho be the canonical map. And given any two-sided ideal in the enveloping algebra, we let this JT be the inverse image in the tensor algebra under this canonical projection map. And then we define the functor from this category defined above here to the category of sets. With this con L applied to any such K algebra R is a set of maps from L to R, where rho is an A tensor K A linear map, mapping this canonical element to the unit and mapping this ideal to 0. And with this definition, you can see that when we apply this to the algebra of endomorphisms of E, then this is the set of what we call J-flat connections on this A module. Then we get the following result. There's an isomorphism of functors. So this defined functor, it's isomorphic to the somehow represented by this enveloping algebra. There is this quotient algebra and this projection map represents this functor. So this determines this pair up to unique isomorphism. So we get for any such two-sided ideal, this somehow plays the role of the curvature of a connection. So a connection, it is flat if and only if the module E is annihilated by the ideal generated by these elements, x tensor y minus y tensor x minus the D product. So the annihilator ideal in this enveloping algebra of this connection, this ideal is somehow determines how the curvature looks like. And then we define the category mod L, comma id, be the category of A tensor A linear maps, mapping this central element to the identity of endomorphism. It's a category of connections with the condition that it's the connection sends this element to the identity. And then there is this theorem saying that given any D algebra, then we let mod U tensor L be the category of left modules on this enveloping algebra. And there is an exact equivalence of categories between this category of connections and the category of left modules on this enveloping algebra. And this functor, it preserves injective and projective objects. And there is a bijection of sets, or it also represents, well, this enveloping algebra, it represents this functor of connections. So there's an isomorphism or bijection of sets, the set of K-algebra maps from this enveloping algebra to the algebra of endomorphisms with this set of connections. So this enveloping algebra, it has the property that any connection, flat or non-flat, mapping this central element to the identity is a module on this enveloping algebra. But this functor, it preserves injective and projective objects. So we can use this result to define X and Tor groups of any type of connection. And this was previously done by Lie-Rinehart for the category of flat connections, using this original enveloping algebra from the 60s. So dually, for the category of this Kosul connection or these other types of connections, we can try to do something similar. And well, this has to be made precise, but we can try to construct the category of connections as a, this is extremely imprecise, category of co-modules on a co-algebra or co-algebra or whatever. And then we can try to do the same dually, and these two approaches, they will, it's a bit like the difference between studying the module of derivations and the module of Kähler differentials. When the ring is regular, these are dual of each other, the double dual of the model of Kähler differentials, then you recover the Kähler differentials. So you do not lose informations. But in the case when the subvariety, when it's singular, you lose information. So these two notions, sometimes they are the same, sometimes they are not the same. If A is regular, it follows the dual of the model of derivations equals the module of Kähler differentials, and we do not lose any information. So if U is any associative unital almost commutative ring with a filtration where U0 is A and where L is U1 and L star is this quotient, and then we assume that the canonical map is surjective. Then we get an exact sequence of, well, it's pre-D-algebras. So it's a D-algebra without this map onto this twist of der by this two-pole cycle. And there is a two-sided ideal. We can also define the enveloping algebra of pre-D-algebra. There's a two-sided ideal and an isomorphism of associative rings. We can construct the enveloping algebra of this D-algebra and realize this associative algebra as a quotient by this two-sided ideal. So as an example, if L star is a Lie-Rinehart algebra, F is a 2 cocycle, and this is this Poincaré-Bikov width isomorphism, then we can construct this the corresponding D-algebra of this Lie-Rinehart algebra and a two-sided ideal, and we can construct this twisted enveloping algebra as a quotient of this, the enveloping algebra of this D-algebra by this two-sided ideal J. And this is, some people call this the Sridharan enveloping algebra. This is an algebra from a paper also in the 60s where Sridharan defined something similar. So we can realize the algebra I talked about in the beginning, this generalization of the Rinehart algebra. This can be constructed using this general formalism. So if F, the 2 cocycle is 0, we get an isomorphism of this, this enveloping algebra of the D-algebra with Rinehart's enveloping algebra. So Rinehart's enveloping algebra is a quotient of this larger enveloping algebra by this two-sided ideal. And also the category of modules on this is equivalent to the category of flat connections on the original Lie-Rinehart algebra. Yeah, a left module on this larger algebra has a flat connection if and only if this ideal generated by these commutators annihilates the module. We can study this larger enveloping algebra, and modules of on this enveloping algebra correspond to connections, any connection, and then the annihilator ideal of this module, it determines the curvature. If we want to study non-flat connections, we can study ideals in this enveloping algebra. So we can use these D-algebras to construct the Sridharan enveloping algebra and the Rinehart enveloping algebra as quotients of this larger universal enveloping algebra. We can also construct Lie-Rinehart cohomology and homology using Ext and Tor groups. So when L star is a projective A module, we can construct Lie-Rinehart cohomology using this Ext group. And this is, so if we define X groups and Tor groups of this larger enveloping algebra, we recover this classically defined groups studied by Rinehart. And we can also, there is an explicit complex computing this. So whenever you have an associative ring, U as L, and 2 modules, you can compute this X group using Hochschild cohomology of this with values in this homomorphism. If K is a field of characteristics, so we get similar statement for the Tor group. You can use Hochschild homology. So it is possible to make explicit calculations of these X and Tor groups. So using the Eilenberg-MacLane spectrum associated to some ring UL, we can also define the topological Hochschild homology of the THHUL. And this theory, this is related to what you've been speaking about on this conference, because Hessel-Holt Yes, use this topological Hochschild homology to construct the zeta function of a scheme of finite type over FP using something Denninger has spoken about, these regularized determinants. So certainly this topological Hochschild homology is, I'm not an expert in this. This is defined, well, it's more category theoretical in nature. But it is, there are some similarities. So we can, if M and N are left modules over this enveloping algebra or any associative ring, we can construct the enveloping algebra of UL, but just by the tensor products. And we can also construct X and Tor groups of left and right modules or bimodules using this enveloping algebra. A problem with homology and cohomology theory is using a lot of abstract machinery, such as totuses, universes, inaccessible cardinals, and so on, is that problems that have a completely elementary formulation may end up having a proof relying on abstract category theoretical results. But if we are able to use some of the constructions in this lecture to give proofs, these proofs will in some sense be more elementary and accesses to the streets and the public. Like cohomology for everybody.
Can I have a question? Could you give me?
No, I don't hear what you're saying.
Okay, yeah, so I want to ask what kind of problem you think you can use this. Of course, you don't know, but you think that you may use.
You have to speak louder. I don't hear.
Okay. Yeah. So can you hear me now?
Okay, maybe you can sit close to the computer.
Okay. Can you hear me?
Try to ask, and then I can try to answer.
Okay, yeah. So, so my question is that, of course, you don't know what happens. That so what kind of questions that you think that your construction can give, like you say, much more elementary and accessible proofs? Can you give like one example? Of course, you don't know what can.
I will come back to this at the end of the lecture. I will try to answer it.
Okay.
Okay.
Yeah.
So, for instance, as an example, if we're given a field of characteristic 0 and a co-commutative Hopf algebra over K, where this the elements in the filtration have finite dimension, and PA, and the graded Lie algebra of primitive elements in A. And there is a theorem of Milnor-Moore theorem from 1965 saying that there is you can recover the Hopf algebra A by using the enveloping algebra of this graded Lie algebra of primitive elements. So V is any K vector space. It holds the tensor algebra has the structure of a Hopf algebra by the co-multiplication map. And the symmetric algebra and the exterior algebra and the enveloping algebra, they are all quotients of the tensor algebra, and they are Hopf algebras. And the enveloping algebra of a D-algebra is also a quotient of this tensor algebra of the K Lie algebra L. We can try to give, we may ask if this quotient has additional structure, such as a Hopf algebra, co-algebra, cogebra, and so on and so on. And then we can ask for a generalization of this Milnor-Moore theorem for this algebra. So it's clear that this algebra has much structure, and that it's interesting to study this structure and its relation to this category of connection and this equivalence. And there are such results recently published for Lie-Rinehart algebras, and these are published in 2019. So this is an active area of research. Well, how much time do I have?
You still have 10 minutes, yeah.
Okay. Yeah. And you know, a lot of the point about this, a lot of the questions you ask for connections and Lie-Rinehart algebras, you can ask these in this more general situation. So if L is a D-algebra and V is an A Lie algebra and A tends to A module, with this commutative property, we define TLW to be the set of extensions of D-algebras, like these short exact sequences, where L1 is a D-algebra, where P1 is a map of D-algebras. Then we say these two extensions, E1 and E2, this is like ordinary extensions. They're equivalent if and only if there is an isomorphism of D-algebras, such that these diagrams commute. This is as usual for extensions. And this is the result, this is an equivalence relation on this set. And we define this X set to be the quotient of this set by this equivalence relation. This is a set, it does not have any extra structure. Then we'll define D-L-W to be the set of triples. Nabla, where nabla is a connection, C is a 2 cocycle, and W is a vector in W with this property. So the curvature of this connection applied to W, it acts as this 2 cocycle psi. Moreover, the connection applied to this central element should act as follows: the adjoint by the minus of this vector. And moreover, psi applied to this canonical element should act as D0 of this vector. And then we define an equivalence relation on the set of all such triples. The two elements are equivalent if and only if there's an element B from L, map from L to W, such that nabla prime is nabla plus the Lie product with B. And also with, well, these elements are related by these three equations. Psi prime is psi plus D1 nabla B plus this Lie product. And W prime is W minus B applied to this central element. And then this is an equivalence relation. And then we define this small x to be this set modeled out by this equivalence relation. And the theorem, which is, it says that if L is a D-algebra, where L is projective as left A module, and W is an A Lie algebra, and A tends to A module, that is, well, commutative, then this there is a one-to-one correspondence of sets between this large X and this small X. Well, the proof, you can find it on arXiv. You are manipulating with these extensions. So this set, it parameterizes all non-abelian extensions of this D-algebra by this A Lie algebra. And you can also prove this for Lie algebra and Lie-Rinehart algebras. For Lie-Rinehart algebras, yeah, I published, no, I put something out on the arXiv, which gives an explicit proof for Lie-Rinehart algebras, but other people have also done similar. So several people have proved this for Lie-Rinehart algebras. Well, so as an application, yeah, for any Lie-Rinehart algebra, L star, and E any connection, then we can use this construction to construct a non-abelian extension of Lie-Rinehart algebras and L with respect to this connection. And this projection map pi, it splits as a map of Lie-Rinehart algebras if and only if E has a flat connection. Hence, this is a bit similar to the Atiyah sequence. You know, the Atiyah sequence, it splits if and only if the module has a connection. But when it has a connection, you get another sequence, this non-abelian Atiyah sequence, which splits if and only if it has a flat connection. There are somehow two such sequences. And you have the same for D-algebras. So if L is any D-algebra, E is a connection, there is this non-abelian extension of D-algebras, which splits as a map of D-algebras if and only if E has a flat connection. So we can, these D-algebras and connection, they are somehow one construction that can be used in the study of all types of connections, flat or non-flat connections. It's kind of one unified language where you can construct enveloping algebras, X groups, Tor groups, extensions, Atiyah sequences, and so on. So somehow you generate a large class of X and Tor groups that may be interesting. And these groups, they generalize algebraic de Rham cohomology groups and singular cohomology groups and other groups that are known to be Weyl cohomology groups. So if X is a smooth complex quasi-projective variety, algebraic variety, E, finite rank locally trivial sheaf on X with an algebraic connection, you get this non-abelian cohomology class. That's kind of the non-abelian Atiyah sequence. A non-abelian Atiyah class. This is zero if and only if E has a flat algebraic connection. And there is this map from this set. This is a set to this cohomology group. Yeah. And then we define the kind of the non-abelian Atiyah class to be the image of this class. And this lives in this cohomology group of this sheaf. And in here, in this same cohomology group, we have this classical Atiyah sequence. Now we have two classes, this non-abelian Atiyah class and this classical Atiyah class living in the same cohomology group. They may be, it may be interesting to study this, the relationship between these two classes, because I have seen it conjecture. I cannot give a good reference, but I saw somewhere that someone conjectured that if X is projective and E has an algebraic connection, then it has a flat algebraic connection. So this class may be related to this, this problem. Well, algebraic de Rham cohomology and Lie-Rinehart cohomology and homology may be computed using this group. We may ask which other cohomology groups can be constructed using this group, such as L-adic et al. Cohomology, crystalline cohomology, rigid cohomology, Chow groups, algebraic K-theory. So if we can construct some of these p-adic cohomology theories, such as, well, L-adic et al. Cohomology, crystalline cohomology, Chow groups, we may get explicit formulas for these groups because we can compute them using this Hochschild complex. And Chow group and algebraic K groups, they're difficult to compute. So if we can, you know, for instance, a cohomology theory such as crystalline cohomology, they are extremely complicated to define. And to prove such results such as Kunnert formulas, they're extremely, they have difficult proofs. And if we can give us kind of a simpler construction of this cohomology, this theory, for instance, using this machinery, the Kunet formula will be immediate, because the Kunet formula, it holds in general for these X groups, because there are X groups of modules on some associative rings, and for such groups you have this Kunet formula. So it could be that it will give some kind of a simplification. Also, if you can construct reasonable p-adic cohomology theories using these X groups, you also get a definition of p-adic homology theories and compatibilities with this cohomology and homology. This is because there are naturally existing compatibilities between X and Tor groups. And all constructions are elementary, and they do not rely on any abstract category theory, no inaccessible cardinals. And there is someone in Paris called Yves André, and he has, at least I believe from what I understand, he has assumed the standard conjectures, and then he has, I have not read this, but apparently he's able to construct all biocohomology theories using flat connections. Again, this is extremely imprecise and vague, but one has to read, he has written a book about this. So I'm not going to comment so much about this. Well, and then there is this so-called Bailinson motivic T-structure conjecture relating T-structures to conjectures on cycles. And one could ask similar questions for these categories of connections and try to relate this to this Bailinson motivic T-structure conjecture. Yeah, well, we want to try to globalize these constructions and relate it to the study of cycles and K-theory and connections in principal fiber bundles and group schemes, and make the theory more and geometric invariant theory, and globalized whole theory. And you can find this online. It's well, 3 papers, 1 in 2015 and 2 in 2019. And the basic reference is homological algebra by Samuel Eilenberg in Carton. Okay, that's it.
Okay, okay. So thanks to Helge for his nice talk. So any question?
Yeah, so I just maybe repeat my question. So you mentioned at the end of your the last maybe previous 2 slides. So you say that you maybe can do something. So did you try to work out this on?
You know, if you come closer to the computer, then I hear you better. Try to come down to this little computer on the table. I think this is better because I can hear very well what Fei Hu says.
Okay, can you hear me now?
Yes, now I hear you very well.
Okay, yeah. So yeah, so I just repeat my question. So in the last previous last 2 slides, so you say that you can do certain, you might be able to do certain such things, and so did you try to work out this on simple examples like curves or surfaces?
No, you know, there is not so much explicit computations of these groups, apart from, you know, when you can compute algebraic de Rham cohomology. So if you take a complex affine algebraic manifold, then you can look at the algebraic de Rham complex of this. You can construct this complex using this machinery. And the cohomology of this is by some work of Grudnik from the 60s. It computes singular cohomology with complex coefficients. So with this machinery, you can recover singular cohomology of a complex algebraic variety. So this you can do, and you can also construct algebraic de Rham cohomology. And this is known to be satisfy this Weil. Well, this is a Weil cohomology theory. But this is a bit the problem in this theory. It's different. One would like somehow to construct, to generate a large class of cohomology theories that can be examples of Weil cohomology theories. And this is the intention of this. Maybe some of these theories can be interesting in this study.
So, okay, so you said you can do it for over characteristic 0. So how about positive characteristic? Can you do something even for very simple
What do you say?
examples like curves and surfaces in positive characteristic? Can you do something?
Well, for any complex algebraic, any affine algebraic manifold over the complex numbers, you can construct a singular cohomology.
Not complex numbers, but I mean positive characteristics. So in over finite fields, can you do something?
Well, then you have to look at maybe a good idea is to study this de Rham-Witt complex. This is one way to construct crystalline cohomology. And
I mean, can you do from your theory? I mean,
now this is in progress. Well, the de Rham-Witt complex is it's a quite complicated construction, but to me it seems to be related to the Rham complex of a connection. It is in some sense a quotient of such a de Rham complex. And then you may wonder if it's possible to construct this de Rham-Witt complex using this formalism. If you can construct the de Rham-Witt complex using this machinery, then you might also get a construction of crystalline cohomology, because this is how this is one way to construct crystalline cohomology.
Okay, thank you. I will leave and I will come back after.
Okay. Is there any other question? So so let's thank Helge again.
Thanks a lot. Thanks.